Hello, everyone. Today, we are going to talk about data discovery at Databricks used with Amundsen. My name is Tao. I'm an engineer at Databricks. I'm a co-creator of Amundsen project. I'm a Apache Airflow PMC. Previously, I worked at Lyft, LinkedIn, and Oracle. And my colleague Tian Ru is also an engineer at Databricks. Previously worked at AWS Elasticsearch. So first, let me talk a bit about data discovery and the challenges. Before we talk about why we need data discovery, let's talk about how to make a good decision. That is, a good decision are all based on data. So who needs data? So the answer is basically anyone, any persona who needs to make good decision needs data, including data analysis, data scientists, product managers, general manager, engineer, experimenter. For example, HR who want to ensure the salary are compared with the markets, politician who wants to optimize campaign strategy, they all need, when they make the decision, they all need to base on some kind of data. So the typical flows of data-driven decision is when the data is first collected, and some analysis will find the right data to use. Then they move on, say analysis needs to understand the data. After understanding the data and explore a bit, some analysis will create a reports, then share the result with the stakeholder. But if the result is not good and found out that they are using the wrong data, they need to go back to step 2 to redo we go through a process until the results are satisfied. And then someone with the result will make a decision. From the workflow, step 2 and step 3 are considered the data discovery and data exploration phase. In fact, for a study, you could see like data science sometimes could spend up to 30% of their time in data discovery. And we could tell like it's not very effective. You want like people to spend as less as possible in the data discovery phase, while spend most of his time doing the data analysis, like finding the right insight from the data. So how could we shorten the time in data discovery? The answer is using a metadata data catalog solutions. So what is data catalog? So it helps a good data catalog help to ease of documentation and discovery. It provides a single searchable portal, display the dependency and lineage between like data entities. It helps to answer lots of questions like where can I find the data? What is the context about this data? Who are the owners? How is the data got created? How frequent is refresh? Is the data trustable? Some kind of these questions. Now let me do a bit introduce Amundsen. So what is Amundsen? In a nutshell, it is an open source project focusing on data discovery and data catalog and metadata. It aims to improve the productivity of data scientists, data analysis, data engineer when interacting with data. Currently, the project is hosted at Linux Foundation Data and AI as an incubation projects with open governance and RFC process. Now, let me do a bit of share some of the notable Amundsen features. Here is the typical homepage for Amundsen. You could see there's a search bar which you could search any entity that have been indexed in Amundsen. Then you could see some of the tag, which is a group some of the important data set based on certain tag. And you could see some of the typical data set that have been used, and I bookmark. Lastly, there's a popular table section showing some of the most used tables in the organizations. Here is a dataset detail page. It includes some of the important metadata information regarding this dataset like descriptions, partition range, owners last updated, frequent use, etc. You're also showing some of the you could also show some of the lineage between dashboard and data sets, saying like which dashboard has been using this data set. You could also search like existing dashboards. Now let's see the dashboard detail page. The dashboard detail page showing like you could show like the owner's last successful runs, even showing like the dashboard preview. On the right hand side, you also could showing like what are the tables that have been using in this dashboard. And you could even search the coworkers and seeing that for the given coworkers, what are the table he own or using. Here are also some of the useful features. For example, like announcement page, it provides a plugin client to support the admin user to surface like some of the new feature for the tool on regarding the new data set. Amundsen could also like configure to as a central data quality issue portal, allow user to report that any data quality related to given data set by connecting, like say, a Jira. Also, you could use for data preview, like the plugin client support like different BI visualization tools like Superset, BigQuery, or Redash. Now, let's talk a bit about how we use Amundsen at Databricks internally. Databricks is a data and AI company. It provides a unified platform for all your workload, including data, AI workloads. It works with more than 5,000 plus customers across the global. It is also the original creators for some of the notable open source projects like Apache Spark, Delta Lake, and ML Flows. So in high level, for Databricks, what is a Databricks Lakehouse? It's support all the structured, semi-structured, and structured data and consume and into a Delta Lake, which could queryable and surface through different tools, including a SQL Analytics, Redash, Data Science Workspace, ML, or ML Flow tool based on different persona. For Amundsen, we are focusing here is how we could surfacing and discover like Delta table or Redash dashboard. Those are the two main features from Amundsen. So previously at Databricks, the internal dataset discovery are still using a static maintained wiki page for golden table or central workspace. And the metadata is in fact easily becomes stale as it's a manual editing. So how do we solve it? We are using Amundsen to improve the data discovery experience. Now my colleague Ken Ru will talk about our Databricks internal deployments.
Next, I will talk about how we deploy Amundsen in Databricks. Our Amundsen deployment consists of three main components, respectively, Amundsen frontend, Amundsen search, and Amundsen metadata, with some customization on top of the open source version. All of them reside in the Databricks control plane as Kubernetes pod. So what is the Databricks control plane? In a nutshell, Databricks control plane is a Kubernetes cluster that contains all Databricks services. For example, authentication service, which is responsible for user login, web app, which controls a workspace UI we see every day, and underlying infrastructures. In contrast, data plane is the environment where our Spark clusters resides to execute different tasks. Amundsen frontend is integrated with Octane to do end-to-end authentication. All Databricks full-time employees have permissions to this step. More information about OpenID connection setup can be found in the Amundsen documents. The front-end service serves as web app portal for user interaction. It is a Flask-based web app whose representation layer is built with React, with Redux, Bootstrap, Webpack, and Babel. We also leverage front-end service to do fine-grained user action tracking. It provides a hook called action logging, which allows us to customize the behavior of usage logs. In our use case, we write these logs to AWS MySQL Server, which can be accessed from Databricks notebooks to do further analysis. Amundsen Search Service Proxy leverages Elasticsearch search functionality and provides a RESTful API to serve search requests from the front-end service. Currently, both table and dashboard resources are indexed and searchable. We use AWS Elasticsearch for convenience. Amundsen Metadata Service currently uses Neo4j proxy to interact with Neo4j graph database and serves front-end metadata. The metadata is represented as a graph model. For Neo4j database, we have our own deployment as a Kubernetes pod in control plane as well. Elastic Blob Store is attached as a persistent volume to store actual data. We leverage EBS snapshot to do data backup. Since we can rebuild Elasticsearch index from Neo4j data pretty fast, snapshot for Elasticsearch is not that necessary. So for the real Kubernetes deployment, we have replicas for front-end, metadata, and search proxy. However, we only have a single Neo4j pod since the EBS-backed system volume is auto-provisioned and EBS does not support read-write menu mode. Amundsen provides a data ingestion library called Data Builder, which supports users to build any source metadata ingestion. By default, people will use Apache Airflow to orchestrate metadata extraction and ingestion. Apache Airflow is an open source platform to author, schedule, and monitor workflows. It helps us to create workflows using Python programming language, and these workflows can be scheduled and monitored easily. However, in Databricks, we use a similar alternative called job service. A job is a non-interactive way to run an application in a Databricks cluster. For example, an ETL job we want to run immediately or on a scheduled basis. We can monitor job run results in the UI using a CLI, calling the API, and email alerts. These characteristics fit perfectly into our use case. For more information about Databricks jobs, please check out our official documents. We leverage Databricks job service to run cron jobs to ingest data into Neo4j database daily and update corresponding Elasticsearch index. Metadata extraction and ingestion logic resides in several Databricks notebooks. We will talk about the details later. Communications between control plane and data plane are done through IP whitelisting. Our data plane cluster has a stable IP address, which is whitelisted in both Elasticsearch and Neo4j services. So previously, we mentioned that for Databricks deployment, we need to do customization for the naive open source versions. So our customization can be separated into two parts. One is configuration changes, and the other is function overrides. For configuration changes, we change the default logo from Amundsen to Databricks. We integrate Amundsen with Octave to do authentication. We change the in-memory SQLite database to AWS MySQL Server to store connection information so that we can scale up our front-end deployment easily. We also do some UI changes, like number of tags, favorite tables to show. For function overrides, we customize the behavior of action logging to track our action. All usage logs will be returned to AWS MySQL Server. We change the heuristics for popular table calculation from totally usage-based to include database reference count as well based on our internal use case. We also changed the tag updating logic to make it searchable immediately after modification. So how do we do the deployment with so many customization? Basically, we submodule the open source version Amundsen service into our own private repo and use it as the base layer. We apply our own local changes on top of it, thus overwrite its original functionality. We will upload the newly built images into the Databricks private Docker repository and use them for our Kubernetes deployment. All our metadata ingestion logic resides in several Databricks notebooks. So how do we do version control over the development process? This is very important, especially when multiple people work on the same notebook. In case we mess up the code, it also allows us to quickly recover from it. Databricks notebooks allow us to sync changes to or from our own Git repo. The configuration is simple. We just need to generate our personal access token, which has repo permission, and grant it to the recent workspace. More setup information can be found in Databricks official documents. Next, I will talk about the metadata surfaced in Databricks Amundsen. It can be separated into three parts: lineage information, statistics, and extended information. I will dive deep into each part later. So first, lineage information. Let's take a look at how lineage information is presented on the UI. On the upper left side, we can see the writer owner of the table. On the bottom left, we can see downstream jobs, downstream users, upstream and downstream tables. For upstream and downstream tables, we can follow the URL to their own dataset page. For downstream jobs, the link can lead us to the actual Databricks jobs. And on the upper right corner, there is also a link pointing to the Databricks job that writes to this table. All the lineage information here are extracted from a pre-created lineage table, which I will talk more about later. So what is table lineage? You can describe the table lineage for our table via a simple graph structure, which shows that a parent-child table relationship can be established by looking at the common workload that ties this parent and child table together. In the graph, we have a workload distinguished by workload ID that reads from an upstream table and writes into a downstream table. This action is performed by the workload puts the parent and child table in direct lineage of each other. Here, you can think of the workload as a Databricks job. This slide shows the details how we generate the lineage table. So the usage log acts as the ultimate truth for all our lineage information. It contains two main tables, read event table and write event table. Their names pretty much explains everything. We need to combine them with the inside table as well, since the latter one contains necessary mapping from pseudo ID to real name. Now we have the raw lineage table. We need to do some further treatment, like normalize table ID by mapping them to the full storage path. We also need to map it back to table names whenever possible. After all the stream processing, we get our final version of the lineage table, which gives us all the necessary information presented above. Next, we are going to talk about statistics information. For column statistics, we run Spark analyze compute statistic command on these data tables, which scan all the rows to do computation for numeric type columns. Then we can run describe extended table to fetch the data computed above. However, since we need to scan the whole table or at least all the rows for specific columns to get the final result, the query itself is time-consuming. This becomes intolerable, especially when we have a large number of tables. One of the mitigation here is to pre-compute these stats in data log so that we can extract the information directly without computing on demand. For frequent users, we get raw usage data from usage logs table as well and do aggregation to get usage count information for each user table pair. Metadata service will generate a list of frequent users for each table based on some customized heuristics we discussed above. We also surfaced data extended metadata in our Amundsen deployment, like mounting point, table properties, and recent table history. We can get this information by describing the corresponding data table or view name. The data extended metadata leverages a feature called programmatic description in Amundsen. The feature is designed that any company could provide its own customized table metadata. Basically, you could provide arbitrary key value pair table metadata and assign it to the table entity, and it will all show up here. Next, I will use Lineage metadata plus data table extended metadata ingestion as an example to talk about our notebook structure. So open source Amundsen data builder library already provides a ready-made data lake metadata structure, and we can easily extend it to surface more information. As shown in the picture, for each script table, we can yield as much information as we want. For example, table owner, downstream and upstream tables, etc. After we have a fully functional structure, we just need to chain it with the Neo4j publisher and the Elasticsearch publisher to publish the data. There are two things worth mentioning here. We use Neo4j search data structure to extract information from Neo4j database and build Elasticsearch index from there, which means that we don't need to snapshot Elasticsearch as long as our graph database data is safely backed up. Second, when we publish data, we will tag them using today's date, which can save us a lot of trouble when cleaning up stale data later. This slide shows the process to clean up stale data. Remember to specify the target nodes you want to delete. Amundsen has native support for dashboards. We integrate it with Redash dashboard, which is also an internal service in Databricks. From the picture, we can see all the dashboards that use the current dataset. We can also follow dashboard link to the detailed dashboard page. From the dashboard page, we can find dashboard metadata like description, owner, create time, last update time from the left panel. On the right side, we have Tables tab, which gives us a list of tables used by the current dashboard. We also have charts belonging to it. We have queries that compose these charts. For these queries, we can easily copy them and even view them in Redash dashboard directly. For each table or dataset, We also provide a useful link that can lead us to the actual dataset page, which shows the table schema as well as some sample data. Lastly, this is our weekly active usage for Amundsen deployment in Databricks. We are gaining adoption internally. Above is a general introduction about Amundsen deployment within Databricks. Hand over back to Tao to talk about Amundsen open source in general.
Thanks, Tianru. So now let me talk a bit about Amundsen open source in general. Since Amundsen was open source like 2 years ago in 2019, it has gained a lot of adoptions. As of today, we have more than 1,500 plus members in our Slack community, more than 2,000 stars for our GitHub repos, and more than 30 companies have been using it in production. And also, it's among the top 20 most popular open source data projects in 2021 based on the recent Data Council survey. And for Amundsen, a few notable RFC or PRs that happened recently. For example, the community provides support using AWS Managed Neptune, which is a managed graph database, as another offering for metadata data store. Same as for MySQL, using MySQL as a metadata store as well. And there are also feature provide a native support for Lineage, showing Lineage front end as well backend. And currently, Amundsen is more like a pool model for ingestion metadata. There's another PR pull request to show how we could do a push model. For other RFC, could be found in the following link. So in summary, we first talk about data discovery in general and how what is the related challenge and how you could solve it in Amundsen. Then we talk about how we integrate Amundsen with Databricks infrastructures internally and how you could do something similar as well. And lastly, Amundsen open source community has been growing tremendously, and we want you to be part of it to solve the data discovery and data catalog challenge together. Thank you.